We've dreamed of reaching Mars for decades, but this time, NASA isn't just going there to visit. They're going to stay. That's the plan that the American government, NASA, and dozens of their international partners have committed to. And assuming they can stick to that plan, what we're looking at is so much more than just landing people on Mars. Landing is incredibly difficult, but it's also not the final challenge. We have never done this before. What comes next is something entirely unprecedented. We need to build on Mars. We need to build a permanent base. Essentially, a small city on an alien world that's 225 million kilometers away from home. And no one is exactly sure how that's going to go. But we do have some incredibly ambitious and innovative new solutions for life on the red planet. First, we need to talk about why building on Mars is exponentially harder than anything we've attempted on the Moon. The Moon is 3 days away. Mars is months. There are no supply lines. There are no rescue missions. If something goes catastrophically wrong on Mars, you're on your own until the next launch window opens. And that could be 2 years away. The Martian environment is also uniquely hostile in ways the Moon simply isn't. Dust storms can engulf the entire planet for weeks at a time, blocking out the sun and plunging surface temperatures down to -80 degrees Celsius. The atmosphere is almost entirely carbon dioxide, so thin that it's basically a vacuum, yet thick enough to create weather patterns that can tear equipment apart. And then there's the distance. A spacecraft traveling to Mars and back will put nearly 2 billion kilometers on its odometer. That's more than 1,000 times the distance of an Artemis mission to the Moon. This isn't just the next step after the Moon. This is an engineering frontier unlike anything humanity has ever faced. But NASA's long-term vision is clear. Under the Artemis program and the Mars Design Reference Mission plans, they're mapping out exactly how a permanent Martian base will rise from the red dust and become humanity's first foothold on another planet. Now, before we can talk about how to build on Mars, we need to figure out where we're going to build. Mars is huge. Its surface area is about the same as all the dry land on Earth combined. So, choosing the right spot isn't just important, it's absolutely critical to survival. NASA is targeting the mid-latitudes, regions like Arcadia, Planitia, and Jezero Crater. These aren't random choices, they're the result of decades of robotic exploration and careful analysis. The criteria are straightforward but demanding. You need sunlight for solar energy, at least during parts of the Martian year. You need flat terrain for safe landing, especially when you're bringing down massive cargo landers carrying habitats and construction equipment. And most importantly, you need access to subsurface ice. Water is everything on Mars. It's not just for drinking. It's for growing food, for producing breathable oxygen, and for manufacturing rocket fuel so astronauts can eventually return to Earth. Rovers like Perseverance and Insight have been paving the way, mapping the terrain, analyzing the soil, and confirming that yes, there is water ice buried beneath the Martian regolith in these mid-latitude regions. This is where the base will rise. A place where science, engineering, and human ambition converge on a landscape that hasn't changed in millions of years. But getting there is the first nightmare. Landing on Mars is an engineering problem that has humbled even the most advanced space programs. The issue is Mars's atmosphere. It's thick enough to create friction and heat during entry, but far too thin to rely on parachutes alone for a controlled descent. You're coming in at 7.5 kilometers per second, and you need to decelerate from that speed to 0 in just a few minutes, without crashing into the surface. The solution NASA has developed is called supersonic retropropulsion. As the spacecraft screams through the Martian atmosphere, it fires powerful rocket engines directly into the oncoming airflow, creating a kind of controlled chaos that slows the vehicle down. It's the same technique that SpaceX has been perfecting with Starship, and it's absolutely essential for landing the kind of heavy cargo that a Mars base will require. But surviving the landing is only the beginning. Once you're on the ground, you're dealing with Martian dust. And this dust is a serious problem. It's fine, almost powdery, but it's also electrostatically charged. which means it clings to everything. Solar panels, spacesuits, equipment, all of it gets coated. The dust is also mildly toxic due to perchlorates in the Martian soil, and prolonged exposure can damage both machinery and human health. So, before we can even think about building habitats or setting up equipment, we need to create solid landing pads to prevent what engineers call dust tornadoes. Every time a rocket engine fires near the surface, it kicks up massive clouds of dust that can travel for kilometers and contaminate everything in the vicinity. The answer, much like on the moon, is to use the local materials. NASA's REDWorks project is exploring ways to 3D print roads and landing pads using Martian regolith. The process involves using lasers or microwaves to heat the soil until it fuses together into a solid, glass-like surface. This technique, known as sintering, could allow us to create infrastructure on Mars without having to transport heavy construction materials from Earth. It's slow work, and it requires a lot of energy, but it's one of the few practical options we have. The idea is that robotic systems will arrive on Mars years before the first humans and spend months preparing the site, melting and fusing the regolith into landing pads, roads, and foundations for habitats. By the time astronauts touch down, the groundwork will already be in place. This is the scale of preparation required before humans even arrive. It's not just about getting there, it's about making sure there's something to land on when you do. Once we've got a foothold on the surface, we need to think about how astronauts will move around and explore. Mars is not a small place, and the base won't be a single building. It will be a network of structures, resource extraction sites, power stations, and scientific outposts spread across several kilometers. That means we need transportation. Enter the Mars Rover Vehicle, or MRV, a pressurized rover concept that's essentially an RV for Mars. Unlike the moon rovers from the Apollo era, which were little more than dune buggies, the MRV is a fully enclosed, life support-equipped vehicle designed to keep astronauts safe and comfortable during extended excursions across the Martian surface. The interior will be pressurized, which means crew members won't need to wear bulky spacesuits while traveling. They can move directly from their habitat to the rover, drive out to a remote site, conduct their work, and return, all without ever being exposed to the harsh Martian environment. These rovers will likely be powered by hydrogen fuel cells or small nuclear reactors, both of which can provide reliable energy even during the long Martian nights and dust storms that block out the sun for weeks at a time. But the MRV isn't just for humans. NASA is also developing autonomous construction robots in partnership with companies like Icon, the same firm that's been working on 3D printed habitats for lunar missions. These robots will be capable of building structures, moving cargo, and even repairing equipment without direct human intervention. The idea is that much of the heavy construction work will be done autonomously, allowing astronauts to focus on scientific research and mission-critical tasks rather than manual labor. This isn't science fiction. Prototypes of these systems are already being tested on Earth, and they represent a fundamental shift in how we approach space exploration. We're not just sending people to Mars, we're sending an entire workforce of robots to prepare the way. Now, let's talk about where humans will actually live. Building a habitat on Mars is not like pitching a tent or assembling a prefab structure. It's about creating a sealed, pressurized environment that can withstand extreme temperatures, dust storms, and radiation, while providing astronauts with everything they need to survive for months or even years. NASA's approach is two-phase, short-term and long-term. For the first missions, astronauts will live in temporary habitats that are pre-deployed before humans even leave Earth. One of the leading concepts is Mars Dune Alpha, a 3D printed habitat designed by Icon. This structure is built using a technique called contour crafting, where layers of material, in this case a mixture similar to Martian regolith, are deposited one on top of the other to create walls, floors, and ceilings. The beauty of this approach is that it uses local materials, which drastically reduces the amount of cargo that needs to be launched from Earth. Mars Dune Alpha is designed to support a crew of 4 for up to 500 days. It includes living quarters, a small laboratory, a workspace, and even a simulated outdoor area where astronauts can conduct EVA training. The habitat will arrive on Mars fully assembled, deployed robotically before the crew lands, ensuring that their home is ready and waiting when they step off the lander. But Mars Dune Alpha is just the beginning. For a truly permanent presence on Mars, we need structures that can last for decades, structures that can grow and expand as the base population increases. That's where Phase 2 comes in. NASA and international partners are exploring several advanced construction techniques, including 3D printing with Martian regolith mixed with sulfur concrete. Sulfur concrete is particularly interesting because it doesn't require water to set, which is a huge advantage on a planet where water is a precious resource. Instead, sulfur acts as a binding agent, and when heated, it can be mixed with regolith to create a strong, durable building material. The European Space Agency has been conducting tests on regolith construction for years, and the results are promising. These bricks and blocks are strong enough to withstand the Martian environment, and they provide excellent insulation against the wild temperature swings between day and night. There's also the possibility of using natural Martian features to our advantage. Mars is riddled with lava tubes, vast underground tunnels formed by ancient volcanic activity. These tubes are naturally shielded from radiation and meteorite impacts, and they offer a stable thermal environment. Some lava tubes on Mars are large enough to fit entire cities inside them. NASA is seriously considering the idea of setting up habitats inside these tubes, using them as ready-made shelters that require minimal construction. It's an elegant solution that takes advantage of the geology of Mars rather than fighting against it. China has also announced plans for autonomous brick construction on Mars, using robots to assemble structures in a manner similar to traditional Chinese architecture, but adapted for the alien environment. The vision here is clear. We're not just talking about a single outpost. We're talking about the foundations of a small, self-sustaining Martian town. Of course, none of these matters if we can't keep people alive. That brings us to life support systems, the technology that will generate oxygen, provide clean water, and grow food on a planet that has none of these things naturally. Let's start with oxygen. The Martian atmosphere is 95% carbon dioxide. Humans can't breathe it, but we can use it. NASA's MOXIE experiment, which stands for Mars Oxygen In Situ Resource Utilization Experiment, has already demonstrated that it's possible to extract oxygen from the Martian atmosphere. MOXIE is a small device about the size of a car battery, and it works by heating carbon dioxide to extremely high temperatures and then using electrolysis to split the molecules into oxygen and carbon monoxide. The oxygen can be stored and used for breathing, while the carbon monoxide can be vented or potentially used in other chemical processes. MOXIE successfully produced oxygen on Mars during the Perseverance rover mission, proving that the technology works. Now NASA is working on scaling it up. A full-scale version of MOXIE could produce enough oxygen to support a crew of 4 and also generate the oxidizer needed for rocket fuel. Water is the next critical resource, and fortunately, Mars has it. Not on the surface, but buried beneath the regolith in the form of ice. NASA's SWIM project, Subsurface Water Ice Mapping, has spent years analyzing data from multiple Mars orbiters to pinpoint exactly where the most accessible ice deposits are located. In the mid-latitude regions where NASA is planning to build the base, there are areas where ice is as shallow as a meter below the surface. Extracting that ice is the challenge. It will require robotic drilling equipment capable of breaking through the frozen soil, melting the ice, and pumping the water into storage tanks. Once you have water, you can do almost anything. You can drink it, obviously, but you can also split it into hydrogen and oxygen using electrolysis, giving you both breathable air and rocket fuel. Water is also essential for growing food. NASA has been experimenting with closed-loop greenhouse systems on the International Space Station for years. Astronauts have successfully grown lettuce, radishes, peppers, and even tomatoes in microgravity. On Mars, the process will be similar but scaled up. Hydroponic and aeroponic systems will allow plants to grow without soil, using nutrient-rich water solutions and carefully controlled lighting. The advantage of this approach is that it's highly efficient and can be done inside pressurized modules, where temperature, humidity, and atmospheric composition can be precisely controlled. The long-term goal is to create a self-sustaining ecosystem where organic waste is composted, water is recycled, and plants provide not only food but also help regulate the air quality by absorbing carbon dioxide and producing oxygen. It's a delicate balance, and it will take years to perfect, but it's absolutely necessary for a permanent Mars base. Now, solar energy seems like the obvious choice. Mars gets plenty of sunlight, and solar panels have been the backbone of almost every robotic mission to the Red Planet. But there's a massive problem: Martian dust storms. These storms can cover the entire planet and last for weeks or even months. During a global dust storm, sunlight is almost completely blocked, and solar panels become essentially useless. NASA learned this the hard way when the Opportunity rover, which had been operating on Mars for 15 years, was finally killed by a dust storm in 2018. The rover's solar panels were covered in dust, it couldn't generate power, and it froze to death during the cold Martian night. For a crewed mission, that's not an option. You can't just shut down life support systems and wait for the storm to pass. The answer is nuclear power. Specifically, compact nuclear reactors like NASA's Kilopower project. These are small fission reactors, about the size of a trash can, that can produce anywhere from 10 to 100 kilowatts of continuous power for years without refueling. Unlike solar panels, nuclear reactors don't care about dust storms, day-night cycles, or seasonal variations. They just work. NASA has been testing Kilopower prototypes on Earth, and the results have been extremely promising. The reactors are designed to be completely autonomous, requiring no human intervention to operate. They can be pre-deployed on Mars, turned on remotely, and left to run for decades. A single 100-kilowatt reactor could power all the life support systems, habitats, and equipment for a small Mars base. If you need more power, you just add more reactors. It's scalable, reliable, and critically, it works in the Martian environment. Rolls-Royce, the same company that builds nuclear reactors for British Navy submarines, is also working on space-based microreactors, bringing decades of real-world nuclear engineering experience to the challenge of powering a Mars base. This is how we ensure that the lights stay on, that the oxygen keeps flowing, and that astronauts can survive even when Mars throws its worst at them. So there it is, our first outpost beyond the Moon, a gateway to the rest of the solar system. If we can figure out how to not just visit Mars, but to live there, to build there, to thrive and expand, then we've unlocked possibilities in space that would never be achievable from Earth alone. This is about more than planting a flag or conducting a few experiments. This is about creating a second home for humanity. Mars is one of the only other places in our solar system where life may have existed. What we learn there will tell us more about our own planet's past and future. It may help us answer the deepest question we've ever asked. Are we alone? If we can build a home on Mars, a place with no air, no oceans, and no life, then there's nowhere we can't go. The Moon was the proving ground. Mars is the foundation. And from there, the outer planets, the moons of Jupiter and Saturn, the asteroid belt, all of it becomes reachable. This isn't just exploration. This is the beginning of an interplanetary civilization. The Red Planet will become humanity's second cradle, and from there, we boldly go where no one has gone before. We've covered the fundamentals of how NASA plans to build a base on Mars, but the reality is that the challenges go so much deeper than just landing, building, and powering a habitat. Living on Mars isn't like living anywhere on Earth, not even in the most extreme environments. Antarctica is harsh, but you can still breathe the air with the right equipment. The deep ocean is isolating, but rescue is theoretically possible. Mars offers none of these safety nets. It's a world where a single equipment failure, a torn spacesuit, or a miscalculation in resource management could mean the difference between survival and catastrophe. So let's dig deeper into what it actually takes to keep humans alive on the red planet, and how NASA is planning to address challenges that go far beyond simple engineering problems. One of the most insidious threats on Mars is radiation. On Earth, we're protected by two things that Mars simply doesn't have: a thick atmosphere and a strong magnetic field. Earth's magnetosphere deflects most of the charged particles from the Sun, and our atmosphere absorbs the rest. Mars lost its magnetic field billions of years ago, when its core cooled, and its atmosphere is less than 1% the density of Earth's. That means astronauts on the Martian surface are constantly being bombarded by two types of deadly radiation: galactic cosmic rays and solar energetic particles. Galactic cosmic rays, or GCRs, are high-energy particles that originate from outside our solar system, probably from exploding stars and other violent cosmic events. They're incredibly penetrating, capable of passing through spacecraft hulls, habitat walls, and even human tissue. Over time, exposure to GCRs significantly increases the risk of cancer, damages the central nervous system, and can cause cognitive impairment. Then there are solar energetic particles, or SEPs, which come from our own sun during solar flares and coronal mass ejections. These events are unpredictable and can happen with very little warning. During a major solar storm, radiation levels on the Martian surface can temporarily double or even triple, creating an immediate life-threatening situation for anyone caught outside. NASA's solution to this problem is multi-layered. First, the habitats themselves will be designed with radiation shielding. This could mean building structures with thick walls made from Martian regolith, which provides excellent protection simply through mass. Remember those lava tubes we talked about earlier? They're not just convenient shelter from dust storms. Being underground means you've got meters of rock between you and the radiation. Some designs propose covering inflatable habitats with several meters of compacted Martian soil, creating a protective shell that blocks most incoming radiation. There's also ongoing research into active radiation shielding, where magnetic fields generated by the habitat itself could deflect charged particles, much like Earth's magnetosphere does on a planetary scale. This technology is still in the experimental phase, but it represents a potential game changer for long-term habitation not just on Mars, but throughout the solar system. The second part of NASA's radiation strategy is operational. Astronauts will have radiation dosimeters with them at all times, constantly monitoring their exposure. Mission planners will schedule surface activities to minimize time spent outside during periods of high solar activity, and there will be designated radiation shelters within each habitat where crew can take refuge during solar storms. It's similar to how submarines operate, with safe zones that crew can retreat to in an emergency. The goal is to keep cumulative radiation exposure below NASA's established safety limits, which are measured in sieverts over an astronaut's career. But here's the uncomfortable truth. We don't fully understand the long-term effects of the kind of chronic, low-level radiation exposure that Martian astronauts will experience. The data we have comes mostly from studies of atomic bomb survivors and nuclear accident victims, which involved very different types of radiation exposure. NASA's Human Research Program is working to fill these knowledge gaps, but until we actually send humans to Mars for extended periods, there will be uncertainties we simply can't resolve from Earth. Then there's the psychological challenge, which in some ways is even more daunting than the physical ones. Imagine being sealed inside a small habitat with 3 or 4 other people for 2.5 years. You can't go outside without putting on a spacesuit. You can't open a window for fresh air. You can't take a walk in nature or feel the sun on your face. Every single thing you do, from eating breakfast to conducting experiments to sleeping, happens in the same confined space with the same handful of people. And if interpersonal conflicts arise, there's no escape. You can't just leave. You're stuck there until the next launch window opens, which could be years away. The psychological term for this is ICE, isolation, confinement, and extreme environment. It's a combination of stressors that humans didn't evolve to handle, and the effects can be severe. NASA has been studying this problem for decades, going back to the early days of the space program. On the International Space Station, astronauts spend 6 months in orbit, which gives us some data, but even that is fundamentally different from a Mars mission. ISS crew members can see Earth outside their window. They can communicate with friends and family in real time. They know that if something goes catastrophically wrong, there's an escape vehicle docked to the station that can bring them home within hours. Mars astronauts will have none of that. Earth will be a tiny blue dot in the sky, barely distinguishable from a star. Communication will be delayed by anywhere from 3 to 22 minutes each way, making real-time conversation impossible. Video calls with loved ones will feel more like exchanging voicemails. And there's no abort option. Once you commit to the surface mission, you're there until the return launch window opens. To prepare for this, NASA has been running analog missions here on Earth. One of the most comprehensive is HISEAS, which stands for Hawaii Space Exploration Analog and Simulation. Scientists and engineers spend up to a year living in a small habitat on the slopes of Mauna Loa in Hawaii, which has a barren, Mars-like landscape. They wear spacesuits whenever they go outside, eat the same kind of preserved and freeze-dried food that Mars astronauts would eat, and deal with the same communication delays. The data from these missions has been invaluable. Researchers have learned that seemingly small things, like having access to a variety of foods or being able to personalize living spaces, have huge impacts on crew morale. They've also identified warning signs of psychological stress, like increased irritability, social withdrawal, or changes in sleep patterns. This has led to the development of new protocols and tools, including AI-powered systems that can monitor crew mental health and provide support when direct communication with Earth-based psychologists isn't practical. But all the psychological preparation in the world won't matter if the basic human needs aren't met. And one of those needs is food. We've talked about hydroponic greenhouses, but the reality of food production on Mars is far more complex than just growing a few vegetables. A crew of 4 will need roughly 2,000 kilograms of food per year. That's a lot of lettuce. Early missions will rely heavily on pre-packaged food brought from Earth, similar to what astronauts eat on the ISS. But for a permanent base, that's not sustainable. You'd need to launch cargo mission after cargo mission just to keep people fed, and that's prohibitively expensive. So, NASA is investing heavily in what they call regenerative food systems. These are closed-loop agricultural systems where waste products from one process become inputs for another. Human waste, for example, can be composted and used as fertilizer. Carbon dioxide exhaled by the crew can be absorbed by plants and converted back into oxygen. Water used for irrigation can be collected and recycled. The challenge is making this system efficient and reliable. On Earth, if a crop fails, you go to the grocery store. On Mars, there is no backup. That's why NASA is experimenting with multiple redundant food production systems. Hydroponics, where plants grow in nutrient-rich water solutions. Aeroponics, where roots are suspended in air and misted with nutrients. And even aquaponics, which combines fish farming with plant cultivation in a symbiotic system where fish waste provides nutrients for plants, and plants filter the water for the fish. Each system has advantages and disadvantages, and the ideal solution will probably be a combination of all three. There's also research into producing protein through alternative methods, like cultivating edible insects or even lab-grown meat. These might sound unappetizing, but they're far more efficient than traditional livestock farming and could provide the complete nutrition that astronauts need. Then there's the question of variety. Human psychology is such that eating the same meals over and over again leads to what's called menu fatigue. People stop eating enough, even when food is available, simply because they're tired of the limited options. This was a problem on early space missions, and it's still a concern today. So NASA is working with chefs and food scientists to develop meals that are not just nutritious and shelf-stable, but actually enjoyable to eat. They're experimenting with spices, sauces, and preparation techniques that can add variety even when working with a limited palette of ingredients. It might seem trivial, but the psychological boost from a good meal after a long day of work in a hostile environment cannot be overstated. Now let's talk about something that often gets overlooked in discussions about Mars bases: waste management. Every human produces waste, and on Mars, you can't just throw it away. There is no away. Every kilogram of waste represents resources that were launched from Earth at enormous expense, and letting those resources go to waste would be not just inefficient, but potentially mission-threatening. So, waste management on Mars is really about resource recovery. Human waste contains water, nitrogen, phosphorus, and other elements that are valuable for agriculture. Through composting and other treatment processes, this waste can be converted into fertilizer for the greenhouse systems we talked about earlier. But it's not as simple as just composting like you would in a backyard garden. Martian habitats need to be sterile environments, and improperly handled waste could introduce pathogens that spread through the crew. So the waste treatment systems need to not just recover resources, but also sterilize the material to make it safe for reuse. Then there's mechanical waste, broken equipment, worn-out tools, packaging materials, all the detritus of daily life. On Earth, we'd recycle or throw this stuff away. On Mars, we need to think about it differently. Some materials can be melted down and 3D printed into new parts. Metals can be recycled. Plastics can potentially be broken down and reformed. NASA is developing what they call in-situ manufacturing capabilities, essentially small factories that can take waste materials and turn them into useful products. This is still very much in the development phase, but it's essential for a self-sustaining base. You can't rely on Earth to send you every spare part you might need. If a critical component breaks and you don't have a replacement, the mission could be over. So, the ability to manufacture replacement parts on-site using recycled materials or Martian resources is a key enabling technology for long-term presence on Mars. Which brings us to something called ISRU, In Situ Resource Utilization. This is the practice of using materials found on Mars to support the base, rather than bringing everything from Earth. We've already talked about using Martian regolith for construction and extracting water from subsurface ice. But ISRU goes beyond that. One of the most important applications is propellant production. The Mars Ascent Vehicle, the rocket that will bring astronauts back to orbit at the end of their surface mission, requires a huge amount of propellant. If we had to launch all of that propellant from Earth, the mission would be impossibly expensive. But if we can manufacture it on Mars, the economics change completely. The leading approach is called the Sabatier reaction, a well-understood chemical process where carbon dioxide from the Martian atmosphere is combined with hydrogen to produce methane and water. The methane can be used as rocket fuel, and the water can be split into hydrogen and oxygen through electrolysis. The oxygen serves as the oxidizer for the rocket, and the hydrogen is recycled back into the Sabatier reactor. This sounds straightforward in theory, but in practice, it requires significant infrastructure. You need power to run the chemical reactors and electrolysis equipment. You need storage tanks for the cryogenic propellants. You need pumps, valves, and transfer systems to move the propellants from the production facility to the rocket. And all of this needs to operate autonomously for months or even years before the crew arrives, because the ascent vehicle needs to be fully fueled and ready to go before astronauts commit to landing on the surface. NASA's design reference architecture from 2009 estimated that producing enough propellant for a single ascent vehicle would require about 40 kilowatts of power running continuously for over a year. More recent concepts have proposed even more ambitious ISRU systems that would fuel not just the ascent vehicle, but also the Earth return stage of the transport, potentially requiring hundreds of kilowatts of power. This is where those kilopower nuclear reactors we talked about earlier become essential. Solar panels alone simply can't provide the reliable, continuous power that ISRU operations demand, especially during the long Martian winters or global dust storms. But ISRU isn't just about propellant. There's also the possibility of extracting metals and minerals from Martian soil. Mars is rich in iron, which could be smelted and used for construction. There are also deposits of silicates that could be processed to produce glass for windows and solar panels. Sulfur, which we mentioned earlier as a component of sulfur concrete, is abundant in some regions of Mars. Even the carbon dioxide in the atmosphere could potentially be used as a feedstock for producing plastics and other carbon-based materials. The long-term vision is that a mature Mars base would be largely self-sufficient, importing only the most specialized equipment and materials from Earth while producing everything else locally. This is decades away from being a reality, but the foundational research is happening right now. Another critical piece of infrastructure that doesn't get talked about enough is communication. On Earth, we take for granted that we can pick up a phone or send a message and get an instant response. On Mars, that's physically impossible. Radio signals, which travel at the speed of light, take anywhere from 3 to 22 minutes to travel between Earth and Mars, depending on where the two planets are in their orbits. That means a simple back-and-forth conversation would involve waiting 6 to 44 minutes between each exchange. For routine communications, that's manageable but annoying. For emergencies, it's potentially catastrophic. If an astronaut is injured and needs immediate medical guidance, waiting 20 minutes for a response from Earth could be the difference between life and death. This is why NASA is developing autonomous medical systems and training astronauts to handle a wide range of medical scenarios on their own. Every crew will include at least one person with advanced medical training, essentially a field surgeon who can handle everything from suturing wounds to performing emergency surgery if necessary. They'll have access to telemedicine systems that can provide guidance from Earth-based doctors. But those systems have to account for the communication delay. Instead of real-time video calls, Mars doctors will send detailed reports and wait for responses. AI-assisted diagnostic tools can help fill the gap, analyzing symptoms and suggesting treatments based on vast medical databases without needing to communicate with Earth. But there's no getting around the fact that Martian astronauts will need to be far more self-sufficient than any astronauts have been before. The communication challenges extend beyond just talking to Earth. Mars missions will involve multiple landed assets spread across potentially hundreds of kilometers, habitats, power stations, ISRU facilities, scientific outposts, and rovers. All of these need to communicate with each other and with orbiting satellites that relay data back to Earth. NASA and ESA have already placed several communications relay satellites in Mars orbit as part of previous missions, and these have worked well for robotic landers and rovers. But a human mission will generate exponentially more data. High-definition video feeds, real-time telemetry from spacesuits and rovers, scientific data from experiments, all of it needs to be transmitted, stored, and eventually relayed to Earth. This requires a robust network of communication satellites in various orbits around Mars, essentially creating a Martian internet. Some concepts even propose using laser communications instead of traditional radio, which could dramatically increase data transmission rates and allow for near real-time video calls with Earth during optimal planetary alignments. Now, all of this infrastructure, all of these systems and technologies, they don't appear on Mars by magic. They have to be delivered, and that's where launch architecture becomes critically important. Getting to Mars requires an enormous amount of energy. A single cargo mission to the Martian surface might require launching 300 to 400 metric tons of hardware from Earth orbit. For reference, that's about the same mass as the entire International Space Station. And you're not sending just one mission. A typical Mars base architecture would require multiple cargo missions to pre-deploy habitats, power systems, rovers, and supplies before the first crew even leaves Earth. Then there's the crew transport itself, plus the Earth return vehicle. plus the Mars Ascent Vehicle. In total, you're looking at potentially thousands of tons of hardware that need to be launched from Earth and sent to Mars. This is where SpaceX's Starship comes into play. Starship is designed to be fully reusable and capable of launching up to 150 metric tons to orbit in reusable mode, or 250 metric tons in expendable mode. The idea is that by making launches cheaper through reusability, you can afford to send the enormous amount of cargo that a Mars mission requires. SpaceX is planning to launch the first uncrewed starships to Mars as early as 2026, primarily as technology demonstrations to test entry, descent, and landing systems in the Martian atmosphere. These early missions won't carry people, but they'll carry cargo and gather critical data that will inform the design of later crewed missions. If everything goes according to plan, crewed missions could follow within the next decade. But here's the reality. Even with Starship, getting to Mars is expensive and risky. Each launch window, which opens roughly every 26 months when Earth and Mars are properly aligned, represents a narrow opportunity. Miss that window, and you wait another 2 years. This creates intense pressure on mission planning and execution. There's also the question of what kind of transportation architecture makes the most sense for Mars. NASA has been studying 4 different propulsion concepts: all chemical propulsion, solar electric propulsion combined with chemical, nuclear electric propulsion combined with chemical, and nuclear thermal propulsion. Each has trade-offs. All chemical propulsion is the most mature technology, essentially a scaled-up version of what we use for lunar missions, but it requires enormous amounts of propellant. Nuclear thermal propulsion is far more efficient, potentially cutting transit times and reducing the total mass that needs to be launched, but it requires significant technology development and comes with political and safety concerns about launching nuclear reactors from Earth. The hybrid systems, which use electric propulsion for the long interplanetary cruise and chemical rockets for the high-thrust maneuvers near planets, offer a middle ground. NASA is actively analyzing all of these options, and the final choice will depend on a complex calculus involving technical maturity, cost, risk, and schedule. One of the most interesting aspects of Mars mission planning is the debate between conjunction-class and opposition-class missions. Conjunction-class missions take advantage of the most energy-efficient trajectories, but they require astronauts to spend about 500 days on the Martian surface waiting for the planets to align properly for the return journey. The total mission duration is around 900 to 1,000 days. Opposition-class missions, on the other hand, minimize the time astronauts spend away from Earth by using higher energy trajectories that don't wait for optimal alignment. These missions can be as short as 600 to 700 days total, but they require significantly more propellant and energy. From a crew health perspective, shorter missions are appealing because they reduce cumulative radiation exposure and time spent in microgravity. But from an engineering and cost perspective, longer missions that take advantage of efficient trajectories might be more practical. There's no clear right answer, and NASA is evaluating both options in parallel. Regardless of which trajectory is chosen, the journey itself will be unlike anything humans have experienced. 6 to 9 months in a spacecraft, traveling through interplanetary space with no possibility of turning back. The crew will experience microgravity for the entire transit, which causes muscle atrophy, bone density loss, and cardiovascular deconditioning. Countermeasures like exercise and pharmaceutical interventions can help, but they can't completely eliminate these effects. By the time astronauts arrive at Mars, they'll be physically weakened, and yet they'll need to immediately adapt to a new gravity environment that's 38% of Earth's and begin conducting complex operations. This is one reason why NASA is considering sending the crew in artificial gravity spacecraft, rotating habitats that use centrifugal force to simulate gravity during the transit. This technology has never been tested with humans in space, but it could be a game changer for long-duration missions. And then, after all of this, after surviving the journey, building the base, conducting the science, and preparing for the return, there's the final challenge: coming home. The Mars Ascent Vehicle will launch from the surface, carrying the crew to orbit, where they'll rendezvous with the Earth Return Vehicle. This is a maneuver that has to work perfectly. There's no second chance. If the ascent fails, if the rendezvous doesn't happen, the crew is stranded. This is why every component of the ascent and rendezvous system will be tested and retested before the crew ever commits to the surface. The Earth Return Vehicle will have been waiting in Mars orbit, potentially for months, fully fueled and ready. Once the crew is aboard, they'll begin the long journey home, another 6 to 9 months in space, knowing that they're finally heading back to Earth. But even returning to Earth isn't straightforward. After spending potentially 2 years in reduced gravity environments, first in microgravity during transits and then in Mars gravity on the surface, the astronauts' bodies will have adapted in ways that make returning to Earth's full gravity extremely difficult. Returning Apollo astronauts, who spent less than 2 weeks away from Earth, still needed assistance walking when they landed. Mars astronauts will face a far more extreme readaptation challenge. They'll likely spend weeks in rehabilitation, rebuilding muscle mass and bone density, retraining their cardiovascular systems to handle Earth gravity. Some effects might be permanent. We simply don't know yet, because no human has ever been away from Earth for that long. So, there it is, the full picture of what it takes to build a base on Mars. It's not just about rockets and habitats. It's about radiation, shielding, and psychological resilience. It's about food production and waste recycling. It's about communication networks and medical autonomy. It's about propellant production and transportation architectures. Every single one of these challenges is solvable, but solving them all simultaneously with the reliability required to keep humans alive 225 million kilometers from home is perhaps the greatest engineering challenge our species has ever attempted. And yet, we're doing it. The technology is being developed right now. The prototypes are being tested. The plans are being refined. Within the next decade or two, if everything goes according to plan, the first humans will set foot on Mars. And when they do, they won't just be visitors. They'll be builders, pioneers, the founders of humanity's first settlement beyond Earth. That base, that small collection of habitats and laboratories and greenhouses on the Martian surface, will represent something far greater than the sum of its parts. It will be proof that we can survive and thrive beyond our home planet. It will be the seed from which an entire Martian civilization could one day grow, and it will be the gateway that opens the rest of the solar system to human exploration and settlement. This is how we become a multi-planetary species. This is how we ensure that humanity's future is not confined to a single world. This is how we boldly go where no one has gone before.